So I was supposed to speak about data distribution in the cloud with Node and Erlang and a few other things. But I changed my mind yesterday when I heard all the talks yesterday. So with Streampunk and everything else, I decided to do a slightly different talk. But we'll start with the data distribution talk, and we'll pivot at some point during the talk, at a random point in time. Okay. So Push is the company I work for. It's a British startup. It was founded in 2006, and we break all of the rules on messaging, basically. Because messaging as designed is wrong for the internet. That's what we think, and we bet the bank on it. Literally. Up until a month ago, I was the VP of Engineering at Push. I introduced something called benchmark-driven development. I've heard it here a lot yesterday. The way we use it is very, very simple. We take working sets, load, stress tests, requirements from our clients, and we run those load, stress tests, and requirements inside engineering. And the rules are very simple. We're latency-driven on the server side. We're responsiveness or timeliness driven on the client side because we're going out to mobile. You can't control latency out to the web. It's impossible, don't try. So we take these working sets and we actually engineer so that we have an improved product release on release. It's very simple. And by doing that, we've actually changed the performance profile of the product to where we're doing, low microseconds now on the server side between a couple of boxes and 8 to 9 million messages a second. Okay, it's on a standard Dell box. And we can do that because we cheat all of the time. Okay. So I'm not a big data guy, although I've worked in a lot of low latency systems. I work in the kind of systems where scale for me doesn't mean big. It means I don't have a lot of time. I'm given budgets for algorithmic trading systems and gambling systems, auction systems, the kind of things that I've been building for the past 10 years, and someone will give me 80 microseconds or less. So I have to get everything done in that time. So JavaScript to Node is probably not a natural choice for me. But then again, neither is Erlang. It happens to be my favorite language. So I love OTP because it gives you standardized behaviors. Everyone in the Erlang community has one way of describing a state machine, and that makes my life easy. It's a single abstraction that everyone reuses. So in Node, you've got create a HTTP server. Everyone uses the same thing. It keeps things easy. Everyone understands. It's awesome. Node should steal behaviors. Right? And bit syntax. I don't like processing bits and strings. It just doesn't make sense. So the language I use pretty much every day is Java. That's what I'm paid to write. I hate it. I love the JVM, though. It's awesome. And I'm liking Node a lot, so we're going to talk about that today. Okay. So I've spent the past month, now that I have a job to play for a living, playing with a new clean room implementation of a virtual machine. So this adds multi-tenancy and isolation to Java. It's pretty cool. Some Aussie guys who set up shop in Dublin, so it's built here down the road on Harcourt Street, and I've been playing with that for the past month. So I can spin up JVM instances inside a single process and keep them fully isolated. So it gives me much higher density deployments. So if I'm going out to the web, to mobile, we don't care about latency anyway. We don't have any control. So you can have much higher density deployments on a standard box. That's pretty awesome. So hello to the Baratech guys. But this is the real world. This is what I do for a living. 174 microseconds, you can get data in and out of a CUDA GPU in your laptop. So you might have an ATI Radeon. If you have a new Mac, I've got an older one, so I've got a CUDA GPU. And I can get maybe 2 million options prices calculated in 174 microseconds. Okay, so that's 2 million equity prices in, 2 million put and call option prices out in a second, or in 174 microseconds. Okay? But I'm from a world of complex event processing. That's where every event is sacred. Okay? Just like in Monty Python. And every single event then, I want to do the minimum amount of work and get it off the wire as quickly as possible. So that's the world I'm in. And that brings me to data distribution. That's what I do today. So traditional messaging, very simple, producers, consumers, it's loosely coupled. It can be broker-based or brokerless. It can be MQTT for small kind of mesh networks, devices, sensor networks. It can be something like AMQP or 0MQ, brokerless or broker-based. I think everyone understands this. Just pick up some enterprise integration patterns and off you go. But it was invented when these were invented, right? When mobile phones didn't fit in your pocket. okay? It's old. I used to support DEC message queues in Motorola and Swords near Dublin Airport. When it broke, I had to drive out and restart the manufacturing plant. 5 lines, that was £2.5 million per hour going down the drain. And the gun was at my head to get the manufacturing plant running again. So just-in-time manufacturing plant. Plant being down equals traffic jam, 6 roundabouts from Dublin Airport. So there were 2 guns to my head. Okay. And fallacies were simple back then, right? The network is reliable, and as we know, it's not. Latency is 0. Unfortunately, it's also biased. So we're going to see that it's not quite true. There are nuances here that haven't been reflected in these standard fallacies and principles that we apply to most systems. Right? So 1992 happened. We started surfing the internet. This was 20 years ago. It was popular and it grew. So the God phone happened in 2007. So touching the internet happened. And we like touching things. We're human. So we took all the things that we know and we love and all the services and skills and specialties and we stuck them into this thing. That's what the cloud is, basically. It's that simple. Then in 2009, this happened. And what I love about this is it's entirely asynchronous. I don't do synchronous blocking or PC. I stopped that when I left Iona 12 years ago. It's devilishly event-oriented. I love this because everything I do is event-oriented. It's per event. Events to me are sacred, right? And it's totally non-blocking. This is music to my ears. It's the only language that took this and says, feck everything else. It's bollocks. That's awesome. Okay? And like all the good things do, it grew and it grew and it grew. I caught up with it last month. So here's my story. Right, fallacies. The network isn't reliable and it's not cost-free. Latency isn't a democracy, it's biased and it hates you. Bandwidth isn't infinite and it's certainly not predictable over the last mile. You can wake up in the morning and on your mobile phone do a bandwidth test, you'll get 0.5 megabits per second because everyone's waking up and checking their email at the same time. 3 o'clock in the morning you get 4 megabits per second. It's biased, it's changeable. Okay? There's not only one administrator, right? So trust is key. And the network is not secure. Neither is the data flowing through it. And I work with idiots that look like the original Doctor Who trading clips of $200 million and think they're awesome. I have to tell them, the speed of light doesn't work like that. I'm sorry. I can't give you what you need. And the transport cost is not 0, right? But what is free is what you avoid doing. That's free. You can run that infinitely fast because you didn't do it. So if you want to run infinitely fast, it's not about how fast your language is. It's about what work you avoid doing in that language, whatever that language is. And that's key. That's what I do. I avoid doing things. I'm the world's laziest person. That's why I write things really fast, because I take all the logic out. That's why it runs fast. It's really simple. It's not complicated. So what, how, and why? We're geeks, so we think what and how. How do we implement this? How do I implement a vector clock? How do I implement a distributed system? The people who pay us think why? What's the purpose? What's the point? What do I get out of it? What's the cost benefit? So we need to put these two things together. Easiest way you build something that answers the why with what and how is avoiding building the whats and hows that they didn't want in the first place. Don't do it. It's dumb. And here's my biggest problem. Right? If I get something wrong, someone loses a trade for $200 million, I get shot. And Twitter is the model that everyone's following because it grew and it grew and it grew and is really successful. So they ignored consistency, availability, and partition tolerance, and they ignored PAC-ELK, which is a nuance on cap. And they introduced IBECMs, right? Immediately inconsistent, but eventually consistent, maybe. Right? IBECM, the Twitter model. We don't want to do that either. That's not allowed in my world. So we want to listen to these nuances and understand the trade-offs, basically. And depending on your working set and what people are doing with your product, whether you're connecting inside or outside of the firewall, those nuances and those trade-offs are different. So it's complex, it's not easy, it's hard. But the trick is, can you do that with something that when you access it, it's convenient and it's easy and it's close at hand. That's basically what I do. Okay? So measure everything. Yesterday, someone said, don't micro-benchmark anyone. I live in microseconds. What do you think I do? I micro-benchmark absolutely everything on my critical path. Okay. So let's break messaging. First thing we can do is solve Mark's back pressure problem. It's really, really easy to solve that problem. You take the queues on the client side of your messaging system, you whack them, and you move them over onto the server side. I wonder what that does. So by virtualizing this queue and moving it over onto the server side, I'll see when there's back pressure in the system because I can't send you data fast enough. If the queue depth is 0, I'm not sending you data, everything's cool. If the queue depth is 1, I'm about to send you data, everything's still cool. If it's greater than 1, back pressure. You can't handle the data I'm sending you. I should conflate. It's that simple. So we broke that rule. Here's another rule. Most people expect messaging systems to be stateless. Ours can be stateful. You can throw data into it. In other words, you just got rid of a layer of caching. Goodbye. So you don't need any of that because the topic actually represents the state. So there's another rule. Broken. Thank you very much. Third thing. Oh, we have data in memory now. That means we can exploit it. We can touch it. We can finger it. We can leverage it. We can take advantage of this state that we have in our messaging. Is it a messaging system or a caching system? Who cares? It's awesome, right? So we can take advantage of this. Rather than sending you a blob, an opaque message, I'll send you a snapshot on connect or on subscribe, and I'll send you deltas of change thereafter. So if you have a list, I will send you the list on connect. And if you add or remove or mutate to that list, I'll send you the changes over time, not the full list. I just dropped your bandwidth utilization by 90%. You're welcome. Right? And behaviors. So this is what we get from Erlang. Right? The great thing about Erlang is you can define what it is to be a state machine, and everyone can use the same notion of a state machine. I don't have the same problem with triangles as someone had yesterday. My head knows what a triangle is. It's a thing with 4 sides. It's a triangle. Right? So you can add these behaviors. You have to decide on the same triangle. He's probably right there. I don't know. I'm not a philosopher, right? So let's assume we all have the same triangle. We can stick a triangle in our messaging system, and then our messaging system can handle triangles, which is pretty awesome. Okay, so that to me is data distribution. It's breaking these rules for good reason, understanding the nuances and trade-offs and where, when, and why you break those rules. And it boils down to these 5 things. We've got relevance, so queue depth, for example, responsiveness. So that is, I should always send data to you that's current. If I have back pressure, that means there's data blocking up. It's becoming less and less current, more and more useless. If I don't block up, I'm always sending you useful information. If that's consistent, awesome, right? Timeliness. So I come from a machine-to-machine world. I'm now working in machine-to-human. You can't see 100,000 messages per second, right? Your eye, when you blink, your vision system shuts down for 200 milliseconds. Goodbye, gone. When you focus on something, it takes 40 milliseconds, okay? So why would I send 100,000 prices per second to a trader? They can't possibly see that much. So if you stick your arm out and you raise your thumbs and you look at your fingernail, that's about as much focus as the human eye has in a monitor at a typical distance, right? So you can cache the hell out of data that you're sending to a human, right? You can send it full bore to another machine. They don't mind. They'll just process it, all right? So that's what data distribution is. And what I was going to talk about was spinning up instances of these things, throwing in logic and getting them talking with Go, Erlang, Java, Node all together. But there's been a lot of spinning things, so I decided to talk on something else. Okay? Why do we send messages, communicate, distribute, or do data distribution? It's about the data. It's that simple, right? That's what we care about. And if you want a responsive performance system, then what you don't do is probably the most important thing. And there's a way of doing that. It's called complex event processing. Okay? It's sugar for streams, basically. So I've got a stream of data. I want to process a subset of it. Or I want to take 2 independent streams, I want to merge them together in real time to produce a derivative stream. I want to combine them in some way. I might want to temporarily pattern match it to something else or look up a cache. So there's 5 basic things you can do in these CEP engines, right? You can call a map function, which is just, say, take a JSON message and return a different JSON message where you've added and removed fields. Processing subsets of the stream. There is splitting or switch case statement or filtering. There's combining or joining, merging and gathering, and there's in-memory lookups to variables of some in-memory state. The most useful one that we add, because you can do expressions in JavaScript, you can solve most of this stuff, are the notion of a window. So I coded windowing up in Node over the weekend, last weekend, so that's when I got to give the talk on. What happened? Okay. We're back. Okay. So a window, an aggregate, essentially allows you to separate what you're streaming over from the actions you're performing on what you're streaming over. So if you've got piped streams or evented.io contributing events in real time, you can do some pretty simple stuff with that. So this talk is actually about EEP, right? Because complex event processing is hard. It's actually not very hard. They just called it complex to scare people away from ever using it. That's why it died. It's actually very, very easy. And you've got most of what you need to do event processing successfully inside Node already. You've got a language, JavaScript, not a domain-specific language. It's a real language. You've got evented.io. It's tyrannically asynchronous. It should be awesome for this stuff. So we're going to take this and we're going to look at windows specifically. So I've got 4 types of windows I'm going to show you. The first is the easiest to implement. It's a tumbling window. Give me 200 events or give me a second's worth of data and then drop out an average. So count some values and give me an average. It's called a tumbling window. So I need to open the window, accumulate values into the window. Think of a queue. You're enqueuing data into this window. And at some point, n events, some time dimension, is going to complete and close the window. Every single event, I'm accumulating the result set. So I'm amortizing the cost of that sum as the events arrive, rather than taking the full hit when I've got all the events in memory. And then I'll close the window and I'll open a new one, so that it doesn't overlap. Very, very easy to implement. So it looks like this. So I described this aggregate function. So I just inherit some class. I've got an init, an accumulate, an init, and a make method. And then I apply it to a window. Okay, so I can, this is how you might normally do it. So this is regular plain old code. Of course, you're not reusing a lot of this in memory state. You're not reusing a lot of the context, and it tends to litter your systems with bad code, right? Because it doesn't describe the notion of I am streaming through a set of data. You're probably also allocating all of this data every time you want to do one of these things, so you can call a convenient function. So it's probably very bad in terms of memory pressure. So we can fix all of that, right? So we can use this aggregate function construction, and that works in the context of a window. You saved all of that memory. It's pretty cool, but you still haven't refactored out this array, and that's where the notion of a window comes in. So in a window, rather than processing data that we have ahead of scheduler or pre-allocated, I take a tumbling window and I queue in a piece of data, and I just keep on doing that on some callback or event loop or context. And at some point, it will trigger a result set through an emit. And if I'm doing an average of a window of size 2, the average of 1 plus 2 is 1 plus 2 over 3 is 1.5, and so on. It's non-overlapping, so these are separate windows. Does everyone understand now what a window is? Put up your hand if I didn't explain it correctly. Awesome. Most people got it. Okay. So these are very similar. The next window type I implemented is a sliding window. So in a sliding window, think of it like a tumbling window, except instead of having discrete chunks of data, I now have every single event that comes in opens a new window, right? So this is n times n squared complexity. It's really bad. Small is good here, small windows. Reality, in 6-7 years of complex event processing, I never used a sliding window size of greater than 2. They're practically useless. So it doesn't matter, right? You don't get hit by it. So in this case, once you have the first n events, every other event will give you an average of the last n events, or the last second's worth, or whatever. Okay? So it looks a little like this. again, you just call in queue. The fact that it is a sliding as opposed to a tumbling window will change the result set. Right? As far as your processing and your coding is concerned, you've got an API, you've got an abstraction. Node can now do windows. Okay? There's periodic windows, so I want to, on a second-by-second basis, deliver some set of results. It looks like this. And we have monotonic windows. We all know people like to change time via NTP, and that breaks distributed systems. So you could use a monotonic clock, give it your own logical clock that you wanted to implement, and you can use that. So we add one method call here, and in some event we'll call tick, and tick talks to clock. It's really simple. So here's an example of a wall clock. It's a monotonic example. Sorry, I had to do that. It's meta-circular and wrong. Okay? And again, exactly the same to use as any periodic clock. Okay? Very, very easy code. You've gotten rid of all these for loops and all those sources of bugs. You have a simple aggregate function that describes what it is to be an average, what it is to be a triangle. Okay? And you can just plug it in. So I'm calling it eep.js. Simple to use. It's got support for aggregates, no combinators because I didn't need them, I didn't write them. I'm going to put it on GitHub soon. It's fast. Most commercial CP engines today, to do this operation, they'll do about 250,000 a second. I can do 34 to 200 times better than that in JavaScript. Right? These are written in Java and C. Right? Because they don't have any mechanical sympathy. It's about the allocations, and that is more about how it's implemented, which is probably subject matter for a different talk. It's simple, it's free. It reduces the flood of events, obviously, because if I have all of these events and I just need the average or some statistic, why send you all the events and you calculate it? I can just calculate it for you and send you the result. Works both ways, client to server, server to client, doesn't matter. And here's the performance. So sliding windows, obviously exponentially degrading. Look at that slope, you could ski down it. Okay, keep n really, really small. When n is small, you're doing about 8 million events per second. Okay, up to 38 million events per second in the tumbling case. So it's fast enough, right? And I'm going to show you just how fast this is. So Java is about an order of magnitude faster, but who cares? And we'll see that that's not important in a second. Okay, my last point, it's not about the language. It's about what you do with the language. So if I have a one producer, one consumer, lock-free, wait-free, full duplex queue, on an Intel Sandy Bridge 2.3 gigahertz, I'll give you the chip details later, I will get between two hyperthreads in C or Java. What's the number? About 300 million events per second between those two threads. If I go between cores on the same NUMA core, the same physical die, the piece of silicon on that machine, I will drop to about 50 million events. Right? If I go across NUMA cores, I'm down to about 30 million events per second. Okay? So the raw speed of your language is irrelevant. It doesn't matter. That's what mechanical sympathy is. It's a relative thing. Right? It's all relative. Relative to what I can get off the wire, you'd be lucky if you can get 10 million 10 to 100 byte messages per second off a wire. Unless you cheat, but that's what I do. And I've got a lot more cheats. So it's fast enough, basically. And it's not about the algorithm, right? It's about your approach to the algorithm on the hardware that you've got in the context that you're working with. It's about context and environment. Because it's not about raw speed. For machine to human or machine to machine. It's about being clever with what you've got, not being dumb with what you don't know because you didn't bother to find out. Okay? And basically you can do it all in Node, which I think is awesome. I didn't know this a week ago. So that's why I changed my talk. Thank you.